All right, friends, you ready for more? Okay. A question that happens a lot after people have gone home and looked at the MO theory study guide is, oh, how much of this do we need to know? And the answer is all of it. But actually, the learning activities will help you realize what you need to know to be successful. The math, all those second derivatives and operators and stuff, that's mostly enrichment, and occasionally there's somebody that wants to know where stuff comes from, and so it's there for that purpose. Your big conclusions from last time are that closer to the nucleus is more stable, that spread out, or having the wave function slope changing more slowly, is more stable. Also, we've learned that electrons are waves. The wave function is the orbital, is the electron in that orbital, and we've also learned that wave functions can have mathematical signs, so that when we see any kind of orbital where we've got different color, we're not thinking about electrons hopping back and forth from one side to the other. Rather, that is what the wave form of the electron looks like. It happens to have positive mathematical sign here, negative sign here, or vice versa. The mathematical sign of the wave function has no physical meaning. It doesn't matter that it's positive or negative, just that it's opposite. And we use this to keep track of places where electron density goes to zero. Obviously, when you change from positive to negative, you've got to go through zero. And places where there is no electron density, that can be really important. So we'll continue to talk about that. We settled on a hybrid of valence bond theory and molecular orbital theory. Remember, in valence bond theory, a bond is two electrons shared between two atoms. For the most part, we're going to keep that view of things. But we're going to remember from MO theory that there are empty antibonding orbitals. And we're always going to have those in the back of our mind. The empty antibonding orbitals are the place where the next electron would go. And putting electrons in an antibonding orbital can break a bond. And that will be important to us a little bit later. All right. Any questions or worries? We'll just open it up. Anxieties of any kind that you want to talk about? Anything you want to know? We just do it all again. Yes. Yes, in fact, some people find it useful to go to the videos that are posted and listen to the lecture in 1.5 or 2 times speed. Get rid of all the uhs and ums and me taking forever drawing stuff. So, okay, anything? All right. Well, let's dive right in with a slightly more complicated molecule. I realized last time I sort of jumped ahead of where we needed to be. Your study guide will take you through the MO and the valence bond theory / MO theory hybrid of various organic molecules, including this one, which is C2H4, or the non-standard name for that people call it is ethylene. Technically it's ethene, but nobody in their right mind calls it ethene. It's ethylene for various reasons, which is why actually in this class we're not going to spend a huge amount of time on nomenclature, because as soon as we know the rules, we're going to break them and we won't care about it. But you have to know the rules before you can break them. So here is ethylene, and without necessarily drawing orbitals, we can think about where each of these bonds comes from. So as an example, what color do we want? This sigma bond between carbon and hydrogen, that's the Greek lowercase letter sigma, carbon and hydrogen bond. And I could say that this comes from overlap of, what kind of atomic orbital from hydrogen contributes here? Sp2, good. Whoa. Sorry, that was the wrong atom. From hydrogen, what should it be? S, okay, good. Not your fault, my bad, sorry. thinking about too many things at once. Right, so you've got the 1s orbital from hydrogen, and then from carbon you've got, spoiler alert, sp2. Now how do you know that it's sp2? You count the number of things around the atom, including lone pairs, and if it's 3, it has to be trigonal planar by valence shell electron pair repulsion. Okay, so we get hybridization from geometry. We look at the atom, how many things surround it, and therefore it has to be trigonal planar. Therefore, it must be sp2 hybridized. So we get a sigma bond from end-on-end overlap of a 1s orbital on carbon with a 1s orbital on hydrogen with an sp2 type orbital on carbon. And, we could fill in the wave function signs to get the idea that we're overlapping the sp3 with the 1s orbital. In phase, you get constructive interference, you get a bonding orbital. That's a sigma bond. Similarly, we could come to the conclusion that this sigma bond between the two carbons comes from overlap of an sp2 orbital on one carbon with the sp2 orbital on the other. All right? And for each of those sigma bonds, though we're not really worrying about it at this stage, there is an empty antibonding orbital. So if we were to summarize the various bonds that we have so far, we've got 4 carbon-hydrogen sigma bonds, and each of those comes from overlap of a 1s orbital on one of the hydrogens with an sp2 on one of the carbons. We have 1 carbon-carbon sigma bond. Okay, and at the same time we're going to have 4 carbon-hydrogen antibonding orbitals, and we'll have 1 carbon-carbon antibonding orbital. If we were to try to draw what each of these looked like individually, say 1 carbon-hydrogen sigma bonding orbital, we'd have a lobe on this side and then a large lobe enveloping the space between the two nuclei and the hydrogen. This is basically what you'd get if you overlapped an sp2 orbital with a 1s orbital side by side. In contrast, the corresponding antibonding orbital is going to have a node in between the nuclei. The wave function sign will change in between the two nuclei. The lobe that's toward the middle, toward the space between the two nuclei, is going to be small because it's been mostly canceled out. So this sort of looks like you put a 1s orbital from hydrogen and you smeared it out to the side, and then you put on an sp2 orbital from carbon, only you flipped it backwards. And it's not important that you be able to sort of figure out where this comes from and why the lobe here on the backside is large. What's important is that there's a node in between the two nuclei. And this is actually the result of the MO theory math. And I guess maybe I said that wrong. I want you to know what the shape of a sigma star is. And I want you to pay attention to the fact that there's a node between the two nuclei. And I want you to pay attention to the fact that a huge portion of that empty sigma star is projecting 180 degrees away from the actual bond. So it's on the back side. That will become important to us later. Now, for the carbon-carbon sigma bonding orbitals, we're going to do exactly the same thing, only in this time we're going to overlap an sp2 orbital from one carbon with an sp2 orbital from another carbon. So here's your carbon-carbon bond. What you would get if you overlapped 2 of those sp2 orbitals together is a nice lobe of electron density in between the two nuclei, smaller lobes on the outside. These 2 atomic orbitals have added together in phase to give us the bonding sigma star orbital. And then for the antibonding orbital, again, you're going to have a node in between the two nuclei, smaller orbital lobes in the space between the two nuclei. We are changing wave function signs, so They need to be opposite colors. We go through 0 as we go from here to here. And then oriented away from the space between the two nuclei, you have these larger lobes. There's also a node at each carbon. That is a general feature of Sp2 hybridized orbitals. And the large lobes project out away from the space between the two nuclei such that if you put electrons here, they would tend to pull the two carbons apart. And that's the sigma star. Okay, now what about relative energy levels? Well, bonding orbitals are always lower in energy than antibonding orbitals. So relative to our break-even point, right, our break-even point is where the 1s or the sp2 orbitals are. The bonding orbitals are lower in energy than these starting orbitals. The antibonding orbitals are higher in energy. Now the one thing, okay, any questions you want to ask about that? Yeah. So when discussing whether orbitals are higher or lower in energy, it's good to have a relative point of comparison. The break-even point is going to be the energy of non-bonded, isolated atomic orbitals. So in this case, you know, if we made an energy diagram and I could put a dotted line here and call this 0, and this would be about the energy of, say, an sp2 orbital on carbon or a 1s orbital on hydrogen. Technically, those aren't exactly the same in energy, but they're close enough that we'll just pretend. That's our starting point. That's where the non-bonded atomic orbitals were. Okay, other questions? Yeah?
Is there a particular reason the bond envelops hydrogen in the bonding type and between carbons it's just in the middle? They're like about the same in energy?
Yeah, the question is there a reason why the bonding orbital for the carbon-hydrogen bond envelops hydrogen, whereas for the carbon-carbon bond, it's mostly the space between the two nuclei? Yes, that has to do with the fact that the carbon-hydrogen bond comes from, how are we going to do this? Move that down a little bit. The carbon-hydrogen bond comes from a 1s orbital on hydrogen, which doesn't have any node and completely envelops the hydrogen, and an sp2 orbital on carbon. So when I bring those two together, and this is, fantastic animation. Whoa, whoa. When I bring those two together, do you see how they overlap and there's no reason for a node at hydrogen because there wasn't one to begin with? In contrast, for the carbon-carbon bond, because we get that from two sp2 orbitals on carbon coming together, then there were nodes at carbon to begin with, and so they'll still be there in the bonding orbital. Okay? All right, others? Yes?
Oh, can I just take a picture?
Oh, yes. You can, feel free to take pictures. I will pose and smile if you want. You can always get these notes after class online. Yeah?
This is just like a small clarification. It said like overlapping in phase.
Yes.
What is in phase?
All right, sorry. Yeah, let's talk about that. Overlapping in phase is shorthand for constructive interference, or rather wave functions adding together, atomic wave functions adding together, terrible penmanship, sorry, with same mathematical sign. That's what we did last time. Where we brought together two 1s orbitals and they overlapped with the same mathematical sign, and therefore we got a bonding orbital. If you do it out of phase, that gives you an orbital where at least at some point in the middle you cancel things out, and that's sort of like destructive interference. Yeah. Okay, others? I saw another hand. Same? Okay, all right. Okay. So if we were to plot on this diagram where the sigma bonding orbitals are, there is a difference in the stability of a carbon-hydrogen bonding orbital versus a carbon-carbon bonding orbital. It's you can look it up in the appendix of your textbook, but it's not important enough that we need to worry about it. So for our purposes, we'll put the 4 carbon-hydrogen sigma bonds here, and we'll put the 1 carbon-carbon sigma bonding orbital here. And then above our break-even point, we're going to have the empty antibonding orbitals. And we're going to remember that the antibonding orbitals are always higher above the break-even point than the bonding orbitals are below it. And that's what really makes them antibonding orbitals. So here are our 4 carbon-hydrogen sigma star antibonding orbitals. Here's our 1 carbon-carbon antibonding orbital. And we know from our Lewis structure that each of those sigma bonds has electrons in it. So we'll go ahead and fill them up with the available electrons. Each of these lines, I haven't told you anything about skeletal structures, presumably because they taught you that in 105, but also because it's pretty easy. So go to chapter 1 or go to the introductory study guide and it will tell you how to do that. Each of these lines represents 2 electrons. So in carbon-hydrogen bonds, you've got 2, 4, 6, and 8. So we filled those up here. You've got 2 electrons in the carbon-carbon bonding orbital. Now, we've left out of our analysis this second bond, which we're going to call the pi bond. It's a carbon-carbon pi bond. Now, if you think about the hybridization of both of those carbons, we'll call them 1 and 2. They're both sp2 hybridized, trigonal planar. An sp2 hybridized atom, an sp2 carbon, comes with 3 sp2 orbitals and then an unhybridized 2p orbital. Just for fun, we're going to pretend like this molecule is in the xy plane, and so the orbital that's left over that we didn't use is going to be the 2pz orbital. And if you think about what an sp2 hybridized carbon looks like, you will have those 3 sp2 orbitals oriented around the carbon, all in the same plane. That's sort of difficult to represent. And then coming out above the plane and below the plane, you're going to have the unhybridized p orbital. Does that seem vaguely familiar to you? You've maybe seen that before. If not, it's in the study guide. So in gray is the plane, the XY plane. This is the 2pz orbital, and these are each sp2 carbons. Okay. Another thing you should know is that sp2 orbitals are a little bit lower in energy than a p orbital. You probably learned in general chemistry that the s orbital is here and the p orbitals are there. And when you do hybridization, you mix these together, you get 3 new intermediate orbitals out, but the p orbital stays exactly where it was. Okay, so we haven't dealt with the empty unhybridized p orbital on each of those carbons 1 and 2. And if we were to draw what that p orbital looks like, again, remembering that the p orbital comes up out above and below the plane where the sp2 orbitals are, the way we draw that here is to just draw the lobe coming out toward us, which I'm making orange, and then there's one in the background underneath the page. And then, of course, we're going to have, and that's the 2pz orbital on one carbon, and then we're going to have another adjacent p orbital on carbon number 2. Okay, does that make sense? If we were to view this from the side, wedges here mean carbon-hydrogen bonds coming out towards you. Dashes mean going back into the page. We would see, oops, I like to use gray for that. These two p orbitals together side by side. Okay. So far we have learned that sigma bonds come from end-to-end overlap of orbitals. In this case, right, with a carbon-carbon sigma bond, the lobes occupy the same space. They overlap end on end. But that's not the only kind of overlap that's allowed. We also have here side-by-side overlap of these two p orbitals. And that's another way you can have an interaction between two atomic orbitals. All right, so we can mix each of these p orbitals together to get the plus combination, which we're going to call a pi bonding orbital. And actually, we're going to draw it just like this, though in principle, I could show you what it actually looks like. I'm going to draw the same structure of the carbon and hydrogen atoms here. The pi bonding orbital is going to have a continuous lobe that hovers above the plane of those sigma bonds, and it occupies the space between the two nuclei. And then we're going to have another continuous lobe below the nuclei, occupying the space between them. Notice that electrons in this, we'll call this orbital a pi bonding orbital. It's a bonding orbital because there's no node in between the two nuclei. There is a node in the plane of the nuclei, just as there is with these starting p orbitals. And an electron is not hopping from above back to below. This is what the waveform of the electron with that energy level looks like. So we're going to call that our carbon-carbon pi bonding orbital. If you want to see what that looks like in a three-dimensional sense, we can come back over here to the Spartan app and make ethylene. Notice, as we've talked about, ethylene is, each of those carbons is trigonal planar. And if we, oops, yeah, that's fine. If we now look, I can show you the pi bond. Sometimes people call this like hot dog buns. I think that's a stretch, but whatever. Okay, and you need to look at that and think, oh, that's just side-by-side overlap of two atomic p orbitals. All right? Questions about where the pi comes from? Yeah?
I understand that. I was just curious on the drawings that you've been doing, where did the antibondings go?
Oh, I haven't shown you the antibonding combination, but I will for this one, yeah. Yeah.
So since the pi bond is higher in energy than sigma bond, does that make it, that makes it less stable, right?
Right, we haven't actually mentioned that yet. the pi orbital is a bonding orbital. That means it's lower in energy than our break-even point. But using what you know about potential and kinetic energy of electrons, do you expect the pi bonding orbital to be higher or lower in energy than these sigma bonding orbitals? Higher is right. Now, explain why that is. Any, got any idea? Yeah, go ahead.
Because they're not as spread out. Like you talked about how we want the electrons to be spread out.
Okay. Not quite as spread out. Good. And what do you notice about distance from the nucleus? It should be farther away, right? In a sigma bond, most of the electron density is huddling in between the two nuclei. So the distance from either of the nuclei is smaller there. That's by definition lower in energy. The pi electrons hover above and below the nuclei, which is fine, but it's not as close. And so we'll see in general, pi bonds are lower in energy than sigma bonds. So if this is our carbon-carbon pi bonding orbital, we're going to put it here, a little bit higher in energy. In terms of how higher in energy, well, some, right? We're not going to look up the numbers. Yeah?
So with the shape where it's the orange on top, purple on bottom, is that where electrons are not crossing over, or are they just rotating around?
So the electrons, you have to think of the electron not as a little dot buzzing around and saying, wee, and then suddenly it transports over here, and then we're going wee over here. No. Actually, the electron is a wave. That occupies all of that.
So all of that being just the purple, or all of that being...
Purple and orange, same time. On the purple side, it might have a positive amplitude. On the other side, it might have a negative amplitude.
Okay. Got it.
Yep. So it's difficult to draw in 3 dimensions what a wave looks like, but basically we would be saying, yeah. So the electron is that whole wave. It happens to be positive there, and it happens to be negative there. Okay, that was mind-blowing to me when I first took this class in the fall of the year 2000. So long ago. Okay, other questions? Yeah.
Just to double check, you said pylons are lower in energy.
Pi bonds are higher in energy, less stable, not as stable as sigma bonds. Yeah, I'm sorry. I think I could sometimes get less stable mixed up with higher in energy. Lower in energy is more stable. Higher in energy is less stable. Yeah.
Yeah, so it might be a dumb question, but how do you determine where the nucleus is to determine like how far away?
Okay, how do you determine where the nucleus is? So in these skeletal drawings, I've shown you where the hydrogens are. The carbons are right here. The carbons are where the lines intersect. And I haven't written out the letter, but I could. And where that letter is, that's where the nucleus is.
So the carbon is the nucleus.
Oh, so if in a bond between 2 atoms, you've got a carbon here, let's say a hydrogen here. Both of those atoms have nuclei. And so they're sharing the electrons. So I guess when I'm saying distance from the nucleus, I mean which nucleus am I talking about for a bond, both of them.
Okay.
Does that make sense?
Yeah.
Yeah. Okay. Yeah.
So I understand like the higher in energy because it's above and below versus in between the nuclei.
Uh-huh.
So is this drawn to kind of scale where it's also more spread out for the pi bond? The electron density is more spread out, or is that just...
Is it also true that the electron density is more spread out for the pi bond than it is for the sigma bond? That might be difficult to see just based on the qualitative way that we've drawn these things. I think that sounds like it's true to me, but I don't necessarily know how to prove it to you. Yeah. All right. Dang it, I just missed an opportunity to, now it's not, my wife tells me when I have to explain jokes, they're no longer funny.
I love democracy.
That's right. That's very good. Right. Okay, so now we need to deal with the antibonding orbital. Let's see. And we're going to get that by simply doing the minus combination. So whereas before we did the 2pz on one atom on one carbon with the 2pz on the other carbon, now we're going to subtract, which means that we're going to put them together but with opposite wave function sign. And you can see that when we do this, there is a change in wave function sign not only in the xy plane, but now also here as we go from left to right across the space between the two nuclei, between the two carbons. We change wave function sign here, we change wave function sign there, and so we actually have a node between the two atoms, and we're going to call this our antibonding pi star. And actually, if you were to sort of draw what this looks like, it would look sort of like this, only if you made these parts of the orbital sort of lean outward. You guys are probably too young to have seen or really worried about or cared about the movie While You Were Sleeping. That was a staple in my family growing up, and whenever I say the word leaning, I think of the line, "Yo, Luce, is this guy bothering you? Because it looks like he's leaning," which was expressing unrequited romantic interest. All right. So that's sort of what it would look like if we go to Spartan. That's what we see. All right. It's an antibonding orbital because there's a node between the two nuclei, such that if we put electrons in this orbital, they would pull the nuclei apart. That's the pi star. Whoops. Okay, and just as the pi orbital is higher in energy than the sigma orbitals, so the pi star is lower in energy than the sigma stars. Yes?
Is there any overlap between the antibonding and the bonding orbital, or are they separated?
It's a good question. Is there any overlap in space between the bonding and antibonding orbitals? Yes, they occupy the same space. Interestingly, with electrons, that's allowed as long as they don't have the same quantum numbers. So, for example, in the bonding orbital, the two electrons can have the same spatial distribution as long as they have different spin quantum numbers. Similarly, the pi bonding orbital can be in the same place as the pi antibonding orbital. They have different energies. It's kind of wild that that's the way it works, but yeah. I will say, though, you may be worried about electron-electron repulsion, and I'll say the Schrodinger equation takes that into account, and in fact, that's why it's hard and in fact impossible to solve the Schrodinger equation analytically for anything that has more than one electron. Yeah?
So going back to the pi star or the
Yeah.
pi antibonding orbital, so that one we created, does it have two nodes, one going this way and one going this way?
Yes.
Okay.
Yep. I feel like you're calling for a timeout or something.
Yeah.
Yes, we have the pi star has, notice what's the same about the pi star versus the pi. both of them have this node in the xy plane. In the xy plane for both of them, electron density is 0. However, the pi star has a node in this direction as well. Yeah. And because the horizontal node, as it were, isn't different from one to the other, we'll basically ignore it. Okay, what else? Other hands? Yeah.
I know this is probably a stupid question, but you mentioned quantum numbers for electrons.
Uh-huh.
What does that mean?
What are quantum numbers for electrons? I'm sorry. Short answer to that, which is not really important for this class, is that when you put all of the things into the Hamiltonian for the Schrodinger equation, potential and kinetic energy of electrons and the nuclei and so on, and then you say, find me a wave function that satisfies this relationship, it turns out that there's only certain wave functions that do that, and they are defined by quantum numbers. And this is where we get the 1s orbital, the 2s, the 2px, the 2py, the 2pz, and then if you go to 3, yeah, and so on. Yep. All right. Others? Frantically erasing stuff. Okay. Yes?
Will we look at the triple bond?
Will we look at the triple bond? Yes. Your study guide does. I'm not going to. Because it's basically the same analysis here, and what we're going to come to the conclusion for a triple bond is we just have one more pi bond flip the other direction, yeah, on its side. All right, yeah.
So if we have an extra pi bond, we have an extra anti-bonding.
That's right. If we had I mean, just real briefly with acetylene, which is the molecule, the simplest molecule with a triple bond, you're going to have two carbon hydrogen sigma bonding orbitals, one carbon sigma bonding orbital, and then you're going to have two carbon pi bonding orbitals. And then there will be similarly two pi stars and so on. Yeah. And all of that will be in the study guide in a fair amount of detail. Yeah.
What's the name of the app used to show us this stuff?
What is the name of the app used to show you some of these things? It's called iSpartan. I bought it years ago. I don't know whether it still exists. It is, I think it's a paid app. But if you want to see orbitals, anything, you can come to my office and ask, and I'll either draw it for you or we'll calculate it really quick using a computer program. And actually, if you really want to dig in, boy, there's a in the chemistry department computer lab, there's a program called Gaussian that you can actually do these calculations in. But that's probably too far that we don't want to go there. All right. Okay, pi bonds. So now that we know this about energy levels and shapes of molecules, we're prepared to make some predictions about reactivity. Okay, here's a major principle in OChem. The highest energy electrons are the most reactive ones. That's maybe a big surprise. Maybe it's not. That's circular reasoning. That's like saying the highest energy electrons are the highest in energy, right? If you've probably learned in general chemistry about Lewis bases, which are electron pair donors, and it probably made 0 sense to you. Like, who gives away electrons? And it's not giving away electrons per se, and we'll talk about that. But Lewis bases are molecules that have high energy electrons. And so we're going to see that if our molecule ethylene were to react as a Lewis base, the electrons that are most reactive are the ones in the pi bond, not the ones in the sigma bonds. This is highly useful in OChem. It's really useful to be able to look at a structure. In fact, it's essential to be able to look at a structure and say to yourself, okay, probably all of the sigma bonds are low enough in energy that they're not very reactive. So probably the business end of this molecule is the pi bond. Probably that's where it's most reactive. We're going to identify the most reactive electrons in many organic molecules, and we'll use terms that organic chemists have used for a long time. Highest occupied molecular orbital. And a lot of the most interesting chemistry happens with the highest occupied molecular orbital. Incidentally, the Spartan app tells us that, right? It actually labels that, right, for the pi bond. And if you want, it tells you in red what the energy level is in electron volts. But similarly, we will be interested in the lowest unoccupied molecular orbital, because this is the place where molecules can be Lewis acidic. You remember learning that Lewis acids accept electron pairs. Well, that was probably confusing because we're not in the business of like throwing a pair of electrons, trading it from one molecule to the other. And that's actually not what happens in organic molecules. But if we had another electron-rich molecule and it was going to interact with our ethylene molecule, the place it would have to do that would be in the pi star. That's the next place electrons could go. All right. So we're going to get good at looking at organic molecules and saying what's the HOMO, what's the LUMO, and that's going to help us predict what will happen. So this is what I mean when I say that the class is going to be a lot easier for you if you can focus on why reactions happen, because then how and what sort of falls out of the analysis and you have to do a whole lot less memorizing. Okay? All right, so yeah, why not? I want to now look at some other organic molecules, and we're going to go through and sort of talk about where each of the bonds might be relative in energy to each other. All right? So let's do something boring and simple. Water. In water, we have two oxygen-hydrogen sigma bonds. We're also going to have two oxygen-hydrogen sigma stars. It's okay if we think of that oxygen as being sp3 hybridized. You don't actually have to think of it that way, but you can, and it's fine. Okay, and so if I count the number of electrons present in water, I have 4 electron pairs, or 8 electrons. If I make an energy diagram for where I expect the sigma bonding electrons to be versus the antibonding orbitals, here's our break-even sort of 0 point. We would predict those two oxygen hydrogen bonds are about the same in energy. We would predict that there are 2 empty antibonding orbitals. What about these lone pairs? I mean, what kind of orbital are they in? Are they involved in a bond? No. So you could say, okay, well, one is in a p orbital, one is in an s orbital, or you could say one is they're both in sp3 orbitals. The distinction won't be important for us, but they are atomic orbitals that are not involved in bonding. But remember, our break-even point is the energy level of atomic orbitals not involved in bonding. So those lone pair electrons on oxygen are actually right here at the sort of 0 starting point. As such, they're actually the highest energy electrons in the molecule. They're not involved in a bond. Bonding stabilizes or lowers the energy of electrons. So, if we have a molecule with lone pairs, those lone pairs are going to be the most reactive electrons in the molecule. Now, there's a lot of you like to play what if with the future to anticipate all possible horrible outcomes. I recommend against that because many of them are completely unrealistic. But you might ask the question, what if you have a molecule that has multiple lone pairs on different atoms? How do you decide whether one's more reactive than the other? And I say, patience, my young friends, we will get there. Okay? It's actually not as bad as you think. But for right now, just looking at a molecule that's relatively simple, if it has lone pairs, okay, those are the high energy electrons. So, let's see if, can we handle this? Maybe we can. Let's imagine a reaction you probably learned about. Go ahead.
Would the Lumo be the sigma star bond?
Yep. Yep. So it's possible that in general chemistry you envisioned something like this happening. Okay? Did you ever envision water dissociating like that? Stop it. It doesn't. Okay? Let me show you what actually goes on. Conceptually, that's not that bad of a way to think, but that's actually not what happens. Okay? So I'm going to draw the highest occupied molecular orbital on water. The two equal in energy lone pairs, I just have to draw one of them. In fact, I could, if you want to pretend like this is in an sp3 orbital, we could draw it like this and that would be fine. Sometimes I don't even bother drawing the orbital for as long as I've got the lone pair written there. So the lone pair on oxygen is the highest occupied orbital in water. It's the highest energy one, right? So if water were going to act as a Lewis base or an electron pair donor, those would be the electrons that would react. Now, what if water were to act as a Lewis acid or an electron pair acceptor? Where is the empty orbital? Which available empty orbital do we have that could accept electrons? The Lumo, which is the sigma star. If we draw that for an oxygen-hydrogen bond, there'd be a lobe on hydrogen, little lobe here, larger lobe there. Interesting. So we have a filled non-bonding lone pair orbital. We have an empty oxygen-hydrogen sigma star. That's the Lumo. We'll call this our Lewis acid because it's got an empty orbital. What would happen if I moved this water molecule closer such that I started to overlap the non-bonding orbital with the sigma star? What do you think that's going to do? Okay, so anytime we overlap orbitals in phase, we get a bond. Okay, between what? Between the oxygen and the hydrogen. Okay, I like that. That works. And in fact, we will show this kind of thing. Do you see the same wave function sign overlap that we're doing there? This is a filled orbital and an empty orbital. Conceptually, what this looks like is we have a sigma star way up here, and we have lone pair electrons here. We're going to mix them together to get a new bonding orbital and a new antibonding orbital. Sorry, that's terrible penmanship. All right. That's going to allow the electrons in the lone pair to move lower in energy because they're going to be involved in a new bond with hydrogen. If we stopped there and we made a new bond with hydrogen, we'd have too many electrons around hydrogen, right? It can accommodate 2, not 4. And because we're dumping electron density into an antibonding orbital, the corresponding bond has to break. So we will use an arrow pushing mechanism that represents 2 electrons here dumping into the sigma star antibonding orbital. We make a new oxygen-hydrogen bond, and the original oxygen-hydrogen bond breaks with its electrons going onto the oxygen to give us a new oxygen-hydrogen sigma bond and a new lone pair that used to be in an oxygen-hydrogen sigma bond. Okay? So, and we actually know what the equilibrium constant for that reaction is. It's about 10 to the minus 7. Maybe. No? What is it? 14? Sorry. Just only off by a factor of 10 million. All right. So that idea, a high energy pair of electrons in one molecule attacking an empty orbital in another molecule, is the great secret of organic chemistry, right? Yeah.
Also, why would the electrons want to move from the lone pair to the anti-orbital, even though, because it's higher in energy?
Right. And so, yeah, the question is what's going on here, because the empty antibonding orbital is higher in energy than this. When you mix 2 orbitals together, this is a general principle, when you mix 2 orbitals together, you get one that's lower and one that's higher. Sometimes they're not lower by very much or higher by very much, but mixing is always 2 orbitals in, 2 orbitals out. One is always lower than you started, one is always higher than you started. And so that's why it's favorable. Because the electrons that used to be in the lone pair are now involved in a bond. Now, you can think of it as the bonding electrons get lower in energy, the antibonding orbital gets a little higher in energy. And you're right, this isn't that favorable. That's why the equilibrium constant is so small. Yeah. Other questions? Yeah.
What does it mean when we're not underneath the OH minus? Those are electrons, right?
Yes, that's lone pair. It used to be in the oxygen-hydrogen bond. Yep, lone pair, LP, sorry. LP. L's and I's are trouble in sans serif font, I think. So, all right. So the first and great commandment of organic chemistry is that Lewis bases react with Lewis acids. We'll have another word for Lewis base. We're going to call that a nucleophile. And we'll have another word for Lewis acids. We'll call that an electrophile. Phile from, I think, the Greek, to love. A Lewis acid, which is an electron pair acceptor, is an electron lover. A nucleophile or a Lewis base is an electron pair donor. It's a nucleus lover because it wants to share its electrons with another nucleus. So the first and great commandment of organic chemistry is nucleophiles react with electrophiles. And the second is like unto it. The HOMO attacks the LUMO. The HOMO of the nucleophile attacks the LUMO of the electrophile. If you can remember that, you'll always know how to get started when I ask you to predict the products of a reaction. Another little secret, which is not that important, well, which is just sort of, it's useful at parties if you want to sound smart. Like, I don't know how many of you have tried busting out, well, you know, all squares are rectangles, but not all rectangles are squares, right? So what I've just shown you here, a Lewis base reacting with a Lewis acid. This is also a Bronsted base reacting with a Bronsted acid. It's all the same thing. All Bronsted bases are Lewis bases. All Bronsted acids are Lewis acids. But not all Lewis bases are Bronsted bases, right? Okay. We'll talk more about that. Don't stress about that for right now. Okay, I think that's a decent place to stop. Let's take a few minutes and we'll jump back in.